So the first method in the chemical vapor deposition is the low pressure CVD. So the figure shows the schematics of the setup needed for this process. So in this process, the gaseous forms, one or more gaseous form of the material which needs to be deposited on the wafers is used. For example, if silicon dioxide needs to be deposited on the wafer, a gaseous form of a silicon compound is used. Now, as the name suggests, it is done at low pressures and high temperatures of the range of 900 degrees Celsius or below. Now, the process setup is shown in the diagram, which is a cross-sectional view. As you can see, it has a reactor chamber which is known as the quartz tube, and this chamber is heated by a furnace, three-zone furnace. The name itself depicts that it consists of three zones and each zone has different temperature range. For example, if the first zone has a lower temperature range, the third zone will be having a higher temperature range. So this is used to deposit different materials on the wafers at different temperature. For example, the deposition of tungsten on the wafers is done at 400 degrees Celsius, whereas the deposition of silicon oxynitride is done at 800 degrees Celsius. So for those wafers which needs silicon oxynitride can be kept at the zone 3, and those wafers which need tungsten can be kept at the zone 1 where the temperature is low. So thus that is how the three-zone furnace is used. It heats the quartz tube. Now the gas is provided through the inlet and there is a pressure sensor which monitors the pressure inside the quartz tube. The wafers are placed on the bottom of the quartz tube and is loaded through the load door. If the pressure inside the quartz tube is higher than the required value, it can be reduced by opening the pump and the outlet. So this is how the experimental or the process setup looks like for this low pressure chemical vapor deposition. So the gas is provided through the inlet. It reacts inside the quartz tube at required temperature maintained by the three-zone furnace and the required pressure maintained by the pressure sensor, and the reaction gives products or the thin film which gets deposited on the wafers placed inside the quartz tube. Thus the source gases react to form the products which gets deposited on the wafers. So we will now see some of the examples for the films deposited on different types of wafers. So the tungsten film of thickness 50 to 450 nanometer can be deposited for 450 to 600 degrees Celsius and 0.5 to 4.5 torr pressure. This is done from the decomposition of tungsten hexacarbonyl at 400 degrees Celsius in argon atmosphere. Now some other commonly deposited materials are SiO2 at 450 degrees Celsius, silicon nitride at 770 degrees Celsius, and silicon oxynitride, which is a complex compound, at 800 degrees Celsius. So the second method of the chemical vapor deposition is the plasma enhanced CVD. The figure shows the process setup for this method. So here it operates at a lower temperature than the low pressure chemical vapor deposition which we seen earlier. Now the plasma generation occurs in this method as the name suggests, and we know that the plasma generation happens when the decomposition of the gases through an electric discharge occurs. The plasma consists of electrons, radicals, ions of the supply gas we provide. Now, due to the presence of the plasma, it enhances the deposition of the supply gas onto the wafers. The plasma enhanced CVD unit consists of a top and bottom electrode, a gas inlet to the top electrode with an RF generator supported by a gas pod and MFC. Here the gas pods are units which can house different supply of gases, and when selected a particular gas will be provided to the gas inlet, and the MFC, the mass flow controller, It controls the amount of gas coming into the gas inlet. Thus, the gas ports can help to select a particular gas into the system, and the MFC will help to control the amount of gas inlet. A heater is present below the bottom electrode, which will control the amount of the temperature inside the chamber. Now, the exhaust valves are present with automatic pressure controller and pressure gauges. This will control and maintain the pressure within the chamber. Now, a system control unit with a personal computer is present to control the overall working of the system. So, the working happens like this. The wafer is placed above the heated bottom electrode, as you can see in the figure. Now the controlled amount of reactive gas is provided through the inlet into the chamber. Now this gas, the supply gas, provides the elements which has to be deposited on the wafers. The electric discharge which we provide through the RF power input between the electrodes, it generates the plasma and it also heat up the wafers. Now the plasma present between the two electrodes, the top and the bottom electrodes, it bombards with the incoming gas molecules, causing the dissociation of the incoming gas molecules. So in this method, the plasma helps to increase the dissociation of the supply gas molecules by bombarding with the other radicals, electrons and ions present in the plasma. Thus, the plasma decomposes the incoming reactant gases, generating ions and radicals, which recombine to form a surface film, which will be coated on the wafer. A single point two color laser interferometer. It will be used to monitor the thickness of the deposited film, and whenever the required thickness is achieved, the process will be stopped. Some of the examples used for the deposition are for silicon deposition, a trimethylsilane gas is used, and for the germanium deposition, germanium gas is used. Germanium is a compound or a gas consisting of germanium ion and the hydrogen ion. Here, the germanium and hydrogen bond is very reactive. Thus, to summarize the process, suitable amount of gas is provided to the inlet. A plasma is developed between the two electrodes by means of an electric discharge due to the RF power input. Now the incoming gas molecules bombard with the plasma particles and it causes the gas molecules to dissociate. The dissociated gas particles as well as the plasma particles recombine to form the required wafer, the required film which is to be coated on the wafer.